So today I'd like to talk to you about mechanical failure, probably the most depressing chapter that we'll cover in materials science, but also one of the most important and leading to some of the most fun testing that you can do in materials science, all right? So the issues that we're going to address in this chapter are how do the cracks that lead to the failure form? How is fracture resistance quantified? What kind of calculations can we do? How do the fracture resistances of different material classes compare? How do we estimate the stress to fracture? And how do the loading rate, loading history, and temperature affect the failure of materials? So first, I think it's important maybe to define fracture. And a fracture is defined as the separation of a material into two or more pieces in response to a static stress at temperatures that are lower than the melting point. And this is something that you would see, for example, in a tensile test if you do that test to failure of the part. Fracture can also occur due to fatigue or creep, which we'll talk about later in a different lecture. And it's associated with the long-term use of the part. And those types of fractures are illustrated in some of the images here at the bottom, where there was a ship that fractured and broke in half due to cyclic loading from the waves, computer chips due to cyclic thermal loading, and then hip implants, cyclic loading from the walking, okay? And I have to say that particularly I've seen a lot of talks on this last type of fracture. Trying to interface a mechanical part with the human body is a really challenging problem from a lot of different standpoints, including tribology, which was where my first training was, the study of friction and wear. Okay, so the first thing that I want to talk about are the differences between ductile and brittle fracture. Okay, now let me first stress that ductile fracture is really preferred in these situations. It's accompanied by significant plastic deformation, whereas with brittle fracture, there's little or no plastic deformation, and it can be catastrophic and quite sudden. So the classification here, there's usually 3 different types of fracture when you do the fracture analysis on a part. You can have a very ductile material, like a plastic, or perhaps a really soft metal such as gold. You can have a moderately ductile material where there's some necking, okay? And then you can have a brittle material where you have basically a flat cross section. So those are the 3 kinds of surfaces that you're going to see. And those are the types of materials. Ceramics often undergo really super brittle fracture, or really, really, really tough metals, okay? Like some of those really high strength steels. Now, like I said, ductile fracture is usually more desirable than brittle fracture. And the main reason for that is that you get a lot of warning before ductile fracture. You can see the necking, okay? You can see it happening, and then you can take steps to mitigate or stop the failure from happening. Okay? Whereas with brittle fracture, there's basically no warning, and the failure is catastrophic, and therefore the crisis is really difficult to avert. Here's an example of pipe failures, different kinds of pipe failures. The ductile failure, another reason that ductile failure is preferred, is that, you know, oftentimes in ductile failure you get one big crack like that, a large deformation and a big crack. Whereas with brittle failure, it shatters. It goes into a lot of different pieces because of all the little tiny deformations. You can get shrapnel flying out from the part, and it can be quite dangerous from that standpoint. So let's talk about the steps of moderately ductile failure. That's actually a really, really common type of failure where you have some necking and then a break across the cross section. Okay, so it goes through these steps. First, you start to see the neck form. Okay, then within the neck, at the most narrow point, you start to create small voids within the material as it gets stretched. Then those voids grow and they start to coalesce inside the part. Then you get some shearing at the surface as those voids grow and coalesce until finally fracture occurs. Now it's worth noting that fracture lines often occur at these 45-degree angles, and that's because of that critically resolved shear stress that we talked about in an earlier lecture in an earlier chapter. Now, fractographic analysis is really common. Oftentimes, scanning electron microscopy images are required of the fracture surface to try and figure out why the part broke in the first place, and what they can do in the future in the processing of the material or perhaps material selection to avoid that kind of thing. Now here you can see in this image on the left, these are from some steels, that you can see that in this particular part there were these little particles, and those particles started the voids. Okay, they were defects, and then the voids started around those defects and probably eventually caused the failure of the part. In this image on the right, you can see the typical structure of moderately ductile failure. If you zoom in, you can see the little holes in the material that were where the voids formed. Okay, so you can see that. And then you can also see that typical 45-degree angle that one sees. This is called a cup and cone structure, because on one side you have a little cup that formed right there, and the other side you have what looks like a cone. Okay, so that's the typical cup and cone structure that results from moderately ductile failure. So here's a naked eye image of what the fracture surfaces look like for moderately ductile versus brittle failure. Here on the left is that cup and cone fracture, which is typical of a moderately ductile fracture surface, and you can see that. And then brittle, however, you can see that it's basically a flat cross section, and that cup and cone structure didn't form because there was no necking in the brittle material. So that begs the question, what do the fracture surfaces look like for brittle materials? What would you get from a fractographic analysis of that material? Well, there's different kinds of things that you might see, depending on what kind of material that you're looking at. For example, of course, most of them are going to have these flat fracture surfaces, and you can definitely see that in these images of this brittle failure. Now, in some steels, you're going to have these V-shaped markings. Okay, and those V-shaped markings are going to indicate where the concentrator of that stress was, where the void or flaw was that eventually caused the brittle failure. You can also see in some parts fan-like patterns that radiate away from the origin of the crack that caused the brittle failure, as you can see in here. Okay, so you have these V-shaped structures, and you have these fan-like patterns that emanate out from where the crack occurred. However, if it's a glassy material, you might just see a smooth and shiny fracture surface, and that would occur in a glass or in some ceramics. If you do an SEM analysis of the surface, instead of just using your naked eye or maybe a visible light microscope, then there's a couple of different things that you would see from these brittle fracture surfaces. You can get either intergranular, sorry, that's a little tough to get out, intergranular, or you can get transgranular fracture. The intergranular fracture is pictured here on the left for two different kinds, this stainless steel and this polypropylene surface. Now, intergranular happens when the part's been through some kind of stress that causes the grain boundaries to weaken. Okay, so that could be maybe a thermal loading or something like that. And you can see here that in this steel, it's definitely broken in between the grains of the material. And you can also see that with this zoomed in view of polypropylene. Now, transgranular means through the grain, and that happens in materials that like to break along certain crystalline faces, okay? And if that happens, then the part can break even through the grain, okay, even within the grain. And that's shown here for this other type of stainless steel, a 316 stainless steel, and this aluminum oxide ceramic, okay? It's important to note that the stress at which real materials break can often be much, much less than the tensile strength cited in textbooks for perfect materials. Okay? And this is because there's going to be flaws within the material, and those flaws act as stress concentrators. Now, this was noticed a long time ago. Da Vinci, 500 years ago, actually observed that the longer a wire, the smaller the load required for that wire to fail. Okay? And that's because the longer the wire, the more likely that it is that you have flaws within the material, right? And those flaws can cause premature failure And of course, larger samples contain longer flaws and more flaws. And here's a little image of what his experiment probably looked like. So let's talk about how flaws can be stress concentrators and how we might quantify that. So here's an equation for the stress at a crack tip, sigma m, okay? So in this image, you can have a crack, and it can either be on the interior of a material, okay, here in the center, or it can be on the edge. Now the length of that crack we'll call A, okay? If it's at the edge, the half crack length is defined as A. Whereas if it's inside, the length of the crack would be 2A, all right? Okay, so that gets plugged in here. Now sigma naught in this equation is the applied stress. A, like I said, is the half crack length. And rho t is the radius of curvature at the tip of the crack. So in other words, it would be the smallest radius of curvature for that crack. So here we have sigma m, which is the stress at the crack tip, is amplified as opposed to the real applied stress. So in other words, the stress can be amplified by some amount called the stress concentration factor, symbolized here as KT. Now KT is 2 times the square root of A over rho t. All right, so that magnifies the stress at the crack tip, sometimes by quite a lot, as compared to the stress that you're actually applying to the part sigma naught. Let's do an example problem. Oh, in a second I'll do an example problem for that. Right now let's do a plot where I show you if you plot along the line of the crack here in that blue line, okay, so this is the blue line that kind of cuts in half that interior crack. In the body of the part, the stress that you're applying is this sigma naught, and then you can see that it approaches that value sigma m right at the crack, so you can see that the stress gets amplified quite a lot, and of course it picks up along the other side for a symmetric crack. Okay, now let's do an example problem. Sorry about that. So what's the magnitude of the maximum stress that exists at the tip of an internal crack having a radius of curvature of 2.5 times 10 to the minus 4 millimeters and a crack length of 2.5 times 10 to the minus 2 millimeters, where a tensile stress of 170 megapascals is applied? So here we're going to calculate sigma m. So we're going to take 2 times 170 megapascals and multiply that times the square root of 1.25 times 10 to the minus 2 divided by 2.5 times 10 to the minus 4 millimeters. When you do that calculation, you get 2404 megapascals. Now that's a factor of 14 larger, so my stress concentration factor, K sub t, is 14, right, as compared to what my applied stress of 170 megapascals is. So you can see that the presence of this crack has magnified the stress by a factor of 14. So basically, if you're trying to design a part, maybe the best thing to do when you do that is make sure that you avoid those stress magnifiers, okay? You want to avoid those sharp corners because it's proportional to the square root of the radius of curvature of that part, okay, of that flaw. So oftentimes you'll see on parts these rounded corners instead of that 90-degree sharp angle because designers are trying to avoid that. Another thing to think about is that cracks having sharp tips are going to propagate easier in a brittle material because cracks having sharp tips propagate easier than cracks having blunt tips, and plastic materials are actually going to deform at the crack tip, and that blunts the crack. Whereas a brittle fracture has a really sharp, and that does not blunt as the crack propagates, okay? There's no ductile deformation that's going on. All right, so brittle failure is going to go more catastrophically and faster, partly because of the radius of curvature of those crack tips. Now, it's also important to understand how this works energetically. There's an energy balance on the crack, and that can help us understand how to design these parts and what to do and calculate the stresses at which failure is going to occur. To understand that, you have to understand something called the elastic strain energy. Now here, what happens is energy is stored in the material as it's elastically deformed. You can think of it kind of like a spring. If you stretch a spring out, you remember from your introductory physics class that the potential energy stored in a spring is 1/2 k delta x squared, where k is your spring constant and delta x is how far the spring is stretched out. So as a material deforms, okay? It's going to act like a spring and store energy within it. Now that energy is going to be released when the crack propagates. How is it released? Well, creation of new surfaces from the bulk actually requires energy. And you might have learned this in an introductory thermodynamics class, that if you're going to form a new free surface, that takes more energy than being within the internal bulk of the material because you have those dangling bonds, okay? Now, we're going to use this information to understand this equation. And this is the criterion for crack propagation in a brittle material. Now, that crack is going to propagate if the crack tip stress sigma n exceeds some critical stress sigma c. Now, sigma c actually depends upon the specific surface energy. In other words, it depends on how much energy it takes to form a new surface within the material. That specific surface energy is gamma sub s, okay? So the critical stress sigma c is equal to the square root of 2e gamma s divided by pi a. E here is the modulus of elasticity, how much energy it takes basically to stretch that out. And then sigma s is your specific surface energy, which is the energy required to form that new surface as that crack propagates. And of course, it's going to be also proportional to the size of the crack. The smaller the crack, the less the critical stress, right? Or the larger the critical stress that it takes. Okay, so that's A. That's that half internal crack length that we talked about earlier. Now, this is an equation for brittle materials. If you want to consider ductile materials, then you have to replace gamma sub s with gamma sub s plus gamma sub p. And gamma sub p is the amount of energy that it takes to plastically deform the material. Remember, brittle materials don't plastically deform, and so you don't have to include that term for them. Let me do an example problem for you that I think will help cement this in your head. If the specific surface energy for soda-lime glass is 0.3 joules per meter squared, compute the critical stress required for the propagation of a surface crack of length 0.05 millimeters. The modulus elasticity for the glass is 69 gigapascals. So here we're calculating sigma sub c, which is the square root of 2e gamma s over pi a. We're going to plug in the numbers that we have for this problem. So we've got the square root of 2 times 69 gigapascals times 0.3 joules per meter squared divided by pi divided by 0.05 millimeters. And when we calculate that, we get 16.2 megapascals. Now note that the stress, when we solve for it, required to propagate that crack is much lower than the modulus of elasticity that's quoted for the glass, right? The modulus of elasticity for the glass is 69 gigapascals. And then you look at this energy, or this stress, 16.2 megapascals, and you think, wow, you know, I'm multiple orders of magnitude below my modulus of elasticity, so I should be safe. However, brittle fracture can occur at stresses much, much lower than the modulus of elasticity because, remember, those flaws are stress concentrators. Now, there's a quantity called fracture toughness. And fracture toughness is a property that measures a material's resistance to brittle fracture in the presence of a crack. And that's because it's really, really important. Real materials have flaws, okay? And so in order to understand how a real material would then behave, you have to have a quantity which takes those flaws into account. And that's the fracture toughness. Now, as you might imagine, metals and alloys have a really good fracture toughness compared to other types of materials. Things that undergo brittle fracture, graphite, ceramics, semiconductors, things like that, have a lower value. And of course, polymers have a wide range, but are still, on average, a little bit lower still. Composites can span the range, as you might expect, as they're a mix, oftentimes, of different types of materials. So they span that range between the metals and the polymers. So let's talk about the equation then for fracture toughness. Here, K is the fracture toughness, and K is equal to y times sigma divided times the square root of pi times a. Now here, y is a dimensionless parameter, and it depends upon the geometry and how that stress is applied. However, it's important to know that, just to get an order of magnitude, y is approximately 1 if you have a small crack in the interior of a thick plate. So that kind of gives you what the order of magnitude that you might expect here is, okay? Now sigma, of course, is the applied stress, and A is that crack half length, okay? Now you're going to get crack growth if your K value exceeds K sub C, okay? And it's also important to understand that the largest, most highly stressed cracks are going to grow first when you have a failure of a part, okay? Now, you can do a couple of things about this. You really want to design against the growth of cracks when you're designing parts. And there's basically two scenarios there. And that's that, first of all, you really can't avoid these flaws that are going to occur inside a part. And due to the way that you have to process the part, that you're forced to process it, you can expect flaws that have a certain size. If you have flaws of a known certain size, then basically you have to tell your user, look, don't exceed the design stress for this part, or you will have failure. And you can tell the user what that is using this equation. In scenario number 2, perhaps you can influence what the size of these flaws are if you do a certain kind of processing, okay? And in that case, you want to design it so that the stress that the part undergoes, right, is okay. In that case, you have to keep the flaws below a certain size for the stress that you know the part is going to have. All right, so that's the two scenarios in how you would design against crack growth. Let me do an example problem for you on this. We have a structural component in the form of a wide plate, and it's to be fabricated from a steel alloy that has a plane strain fracture toughness of 77 megapascals times the square root of meters and a yield strength of 1400 megapascals. The flaw size resolution limit of the flaw detection apparatus is 4 millimeters. So if the design stress is 1/2 of the yield strength and the value of y is 1, determine whether a critical flaw for this plate is subject to detection. Now there's something that maybe I forgot to mention. When you have a fracture toughness value, the units on it are really strange. And that comes from that equation for K. Let me show you that equation for K again. Okay, remember y is dimensionless, sigma is your stress, and then you have that square root of a length. So the units for K are kind of weird. It's going to be stress times the square root of a length, okay? Megapascals times the square root of meters. It's a weird unit. It's worth noting. But back to the example. Here we've got this A max, okay? And what we want to know is A max going to be smaller than our detection limit? If so, we have a real problem here and we need to think about it, okay? So going back to that equation, we can rearrange that equation for K and solve for A, all right? When we do that, we get that A has to be less than 1/pi times the square of our plane strain fracture toughness K sub C divided by y and then divided by the design stress, okay? So when we plug in for those values cited within the problem, we get 1/pi times 77 megapascals square root of meters divided by 1 times 700 megapascals, okay? Now note that even though the units are weird, it's going to work out. The megapascals on top cancels out with the megapascals on the bottom. And then also we're going to square this, and so that root meters becomes meters when it's squared. So we're going to have units that work out. It's worth mentioning. Okay. So when we solve this problem, we get 0.00385 meters, okay? Remember that our limit for what we could see was 4 millimeters. And so, no, actually, in this case, it wouldn't be subject to detection. And what that means is that you could have critical flaws and not find them, which is a really bad situation to find yourself in. So you need to do a couple of things. Perhaps you need to decrease the size of the flaw that you can detect, or maybe you need to change your processing technique so that there's no way that you would have flaws that are that small. Now, this is such an important problem in materials science that the ASTM has developed a number of standardized tests for fracture toughness. Now, in all of these tests and all these kinds of tests, what you do is you create a defect and then you bang on it and see how much energy or how much stress it takes to make that part break given that defect, okay? Now, one common test in the United States is the Sharpie V-notch test, and that's what's shown here. You can see that you have a bar of a material, and in that material you've created a defect in the form of a V-shaped notch, okay? And then what you do is you apply a stress right at that notch and see how much energy it takes to break it. Now, one way to do that is just to borrow something from your introductory physics class, okay? So basically, you have a hammer that you pull back to some initial height, which I'll call h, okay? Now, when you pull that hammer back to that height, then you know that the energy, the potential energy stored in that system is mgh. U is equal to mgh is the gravitational potential energy, where m is the mass, g is the acceleration due to gravity near the surface of the Earth, 9.8 meters per second squared, and h is the height above your origin. In this case, your origin is where you're going to place that part. And so you're pulling your hammer back to some height h above the minimum height of the part. Now you can see that you've got a hammer that's got a notch cut into it, and it's designed to swing and strike right at that V-shaped notch that you've created, okay? So as this hammer falls, it's going to lose that energy, okay? It's going to lose that amount of energy. And all of the mgh energy that it has initially is converted to kinetic energy at the bottom of the swing. And then that kinetic energy goes into breaking that part. When it goes into breaking that part, some of the initial gravitational potential energy is lost in the system. And what that means is that the hammer isn't going to swing as high on the opposite side. It's going to swing to some lower height, we'll call it h prime. And then you can calculate rather easily the amount of energy that it took to break the part. You just subtract the initial gravitational potential energy, mgh, minus the final gravitational potential energy, mgh prime. And then you subtract those two things, and that energy difference is the energy that it took to break that part. And that's how you figure out what the energy of the break is. Okay? So this is one of the standardized tests the ASTM has developed. It's pretty easy to do and easy to read and interpret. And then, of course, you would do this test many, many times to get an average value for the parts that you're putting out. Now, like I said, some of these tests that they do in material science are some of the most fun that material scientists get to have, I think. And so there's all kinds of great videos out on the internet of people breaking stuff on purpose for the sake of safety. And here's one link for that, but if you Google it, you should find it. You should really watch these, by the way. They're a lot of fun, and maybe put you on a future career path for all you material scientists out there. Now, this is a really big deal. There's something called the ductile to brittle transition temperature, okay? And that is, for some materials, the temperature at which the material goes from a ductile fracture situation, which is what's preferred, to a brittle fracture situation, which is really catastrophic and maybe not so great. And so this is something that you need to think about when you're designing parts that go through a stress. And there's been a lot of examples throughout history of people maybe not thinking about this or not understanding it, and the catastrophic failures that resulted. Okay, so let's talk about this a little bit. If you remember, high strength materials don't stretch much when they're pulled, okay? And they undergo brittle fracture at a certain force. Now, more ductile materials are going to stretch before they break. So which kind of materials are which? Well, low strength FCC metals and most HCP metals stay ductile and don't experience that transition. And that's the top curve here for things like copper and nickel and so on and so forth, okay? Now, the other kinds are high strength materials. They stay brittle, okay? And they're going to be here on the blue curve. So you know what they're going to do. But there is a certain class of materials like BCC metals, like some of the low strength steels. And what's going to happen is they're going to start out ductile, which is the preferred range, but then they're going to transition to a brittle kind of fracture with a change in temperature. So as the temperature drops, they start out ductile, and that's the curve in pink here, but then they drop down and become a brittle fracture transition. Okay? For example, iron, it can do that. And then some of the steels. So you really need to do these tests, these fracture tests, at a range of temperatures, okay? And make sure that you've not got a ductile to brittle transition temperature kind of problem when you design some of these parts. You really want to avoid that. And here's a couple of examples why, okay? Pre-World War II, the Titanic, and in World War II, the Liberty ships. Now what happened here was that these steels were used to create these ships, and they have ductile to brittle transition temperatures that are just below room temperature. And so what happened was, especially here, this World War II Liberty ship, this was just in regular service. This didn't happen as a result of a battle or anything like that. But the fact that it went through this ductile to brittle transition temperature, and then you have sort of a cyclic stress that's applied because, you know, these ships are always getting pounded due to conditions in the seas, and then eventually catastrophic failure just resulted. The ship broke in half. I mean, that's something that you really want to avoid. Now, if you are thinking about this and you're wondering what maybe you can do, remember that increasing the carbon content is going to raise the Sharpie V-notch transition temperatures of steels, but decreasing the grain size has been found to lower that transition temperature, okay? So what you want to do is you want to lower that transition temperature until it's a temperature that you don't really commonly encounter in your use for the part. All right? Well, we're going to pick up there with our next lecture. I hope you enjoyed it, and as always, let me know if you have any questions.